So I can present now, right?
Yes, yes.
Well, just a second. Is my screen available now?
Did you put on present now?
Yes. So I think
Can I?
there's coming. Will you allow meet.google.com to see your screen? So
Yeah. Just click on that window and click share. Yeah.
okay.
Then
Okay, so it's available now.
yeah.
Okay.
Yeah, we can see.
Okay, so before I begin, I just wanted to say a bit of a disclaimer that I just made this very fundamental, and there are some issues where there are a lot of mathematical derivations, because that's how observational astronomy is concerned. But I have tried to provide a very brief and basic overview as to how those are used in the context of observation. Okay, so and there might be some topics which I might not have covered because I think that I still don't have a very concrete idea of it, and I guess while during the seminar you guys can help me about it. Okay, so can I begin now?
Sure, and let's keep it interactive. If anyone has any inputs or questions, we can
Okay. So I basically start this seminar with just a very basic incident. I got to know about this from one of my senior fellow mates. So I think in school we basically study about spectrum in class, I guess 7 or 8 in general school. So in one of the classes, I guess in my place, one of the teachers came and drew the spectrum diagram on the board, and one of the students got up and then said, "Hey, this is the image from the dark image side of the moon album." And the teacher got so confused. He said, "No, this is the image of the spectrum." So this confrontation went on for like about an hour, and then the teacher finally got to know that this is the cover pic from one of Pink Floyd's major album, which was released in 1973, because it dealt with a lot of issues like mental health and all. So that's the main story, and then now I'll begin with the outline of the talk. Basically, I'm going to start a bit with history, then the fundamentals like how we got to spectroscopy, the applications majorly in context of astronomy, and then where do we stand today in terms of spectroscopy. Okay, so we all know that Isaac Newton was the person who began his journey in the field of optics, and obviously in other fields too, and he was the one who discovered spectrum, and then famously now also known as the corpuscular theory of light, and which also gave birth to the Newton optics. A lot of us know that Fraunhofer was the one who worked a lot on dark lines of the sun, so often from the spectrum of the sun. But interesting, it was Professor Hyde Wollaston who was the one who discovered dark lines. Okay, we all might not know about him, but he was the one who actually designed the motor upon which Michael Faraday, he made his laws of induction. Okay, so after Hyde discovers dark lines, it was in 1814 when Fraunhofer began to, he discovered these dark lines and began to study about this, and he started making catalogs of these dark lines. So I guess he made catalogs of about 500 to 600 lines. The data is still not yet very much confirmed, but as sources say that about those number of lines Fraunhofer calculated, and it was after Fraunhofer, people like Kirchhoff and Bunsen, they basically analyzed that why are those dark lines present in the spectrum of the sun, and we all know today that it's because of the absorption line elements. I will leave that to, I will talk about absorption in a few slides later. Here is also an image by which was done by Fraunhofer, and you can see a few of the dark lines and also the peak at the yellow line. Okay, and then this is the spectrum. We all know that white light, when it encounters a prism, it gets broken down into its individual components. Now the reason why it happens is because all of those components in the white light, they all have got different wavelength, and we know that how the wavelength is related to the velocity. In terms, the velocity is related with the refractive index. So when the white light encounters a prism, all of those components, they receive a change in refractive index, and as a result of that, all of those individual components, they get deviated out depending on their wavelength. So you can see the one with the largest wavelength is deviated the least, and the one with the least wavelength is deviated the most. And you can see the entire spectrum, and this entire process is categorized as dispersion. You can also see the spectrum of the visible light, which you can see in the nanometer range. Okay, and then after the spectrum was discovered, around just at that time, a lot of people, a lot of the experimentalists discovered a series of spectral lines of hydrogen, and that was basically in the Balmer range. Now the Balmer issue comes very much later on, because a lot of the Balmer region, you can see that it falls in the visible range. All other ranges, they are basically out of the visible range of the human eye. So a lot of these spectral lines were visible. A lot of people were working on that, and there was no concrete theory as to why those lines were visible. So it was the great work of Niels Bohr, who actually, in order to explain those spectral lines, he put forward his theory of the hydrogen atom. The Bohr model is not used now anymore because it only applies to simpler models like the hydrogen atom, but the basic ideas which it implemented was very much crucial into understanding why we have absorption lines and emission lines and so on. So we all know that his basic concept was that electrons in an atom, it revolves around the nucleus in certain orbits, and each of those orbits they have got a specific amount of energy, and because of the energy in those orbits, the electron also have that particular amount of energy. Also, the orbits did not have just any random orientation. They all have orientation based on the angular momentum of electron, which is basically an integral multiple of h times 2 pi. Just like we have stairs, so stairs, they do not just have any random height of it. We can put feet on the stairs at only a particular fixed width and height. And then the most interesting and the most challenging aspect of his work was the electron transition, where the electron jumping, the electron moving from the lower energy level to a high energy level leads to an absorption of photon. At the same time, the jumping of electron from the higher to the lower energy level leads to the emission of photon, and this was the most integral part of his work. You can see that the equation in the second part looks very similar. Okay, and this equation is basically inspired Niels Bohr from the work of you can see here the energy levels and how they are transitioning from the lower to the higher and from the higher to the lower. Okay, and you can also see for which wavelengths we have the values. As I said, the equation out here looks very similar, and this was basically inspired by Rydberg's equation. Now Rydberg's equation is very crucial because it will further help us to understand the properties of the Balmer lines. Okay, and this was basically done by a Swedish physicist, Johannes Rydberg, in 1913, and which is also used as a very crucial term in the field of quantum mechanics. I'm not emphasizing much on quantum mechanics because that's not what we're dealing out here. So this equation holds quite significance in Niels Bohr's theory. Okay, and this is the main priority over here. Balmer series is basically, as I said, it's basically the visible spectrum of the hydrogen spectral series, and this is the only series which has a huge implication in the field of astronomy. You can see H alpha, H beta, H gamma, H delta. Now these are very much important into understanding various astrophysical objects, whether they have an abundance of hydrogen, what kind of hydrogen. So this is very, very important in understanding the abundance of hydrogen into various astrophysical objects, and this is where we get to understand whether any particular star or any particular planet or exoplanets, whether they have those properties. Okay, and as I say, we get also known as H alpha or the H beta lines, and in various galaxies they also have like the active galactic nuclei. Active galactic nuclei is not a galaxy, it's basically a kind of you can say an active supermassive black hole at the center of the galaxy, and its interaction with the surrounding material over here is also known as the active galactic nuclei. You would also hear in various research papers and various articles that they refer as H1 line, H2 line. So H1 line, H2 lines are basically the neutral atom. When someone refers to H1 region, it basically refers to the abundance of neutral atoms. When H2 region is mentioned, it means whether the region or whether the atom is single or doubly ionized, H3 regions and so on. And that's how we have so many important lines in astronomy. Okay, and then we comes to the Wien's law. which is very much crucial into understanding the various properties on classifying various stars based on their temperature. Okay, the very basic formula, we know that the peak of any particular wavelength is given by the constant B divided by the temperature, and how the lower wavelength light is categorized as the most hotter objects, and how the cooler objects is categorized by the longer wavelength. So you can here see how the intensity of light is characterized as the basis of the various colors of the hot object and the cold object. So sometimes when astronomers they look in the night sky and they analyze images after taking through a telescope or observatory. So as a first implication, these kinds of graphs help them to understand the kind of wavelength or the kind of emissive wavelength that particular astrophysical source emits. Okay, this is some of the major applications. You can see based on the temperature, as the temperature becomes lower, it shifts to the right hand side, and as the temperature increases, it is shifting to the bluer part. So that's how the application of the Wien's law is important. Okay, so now we come to the various Kirchhoff's laws, which is kind of very important for us. So for the normal spectrum, this is a continuous spectrum. There is no absorption or any kind of emission taking place, and you can see how the intensity is varying in terms of the wavelength. Okay, you can see it's quite normal for us to understand. And then we have the most interesting aspect, which is the Kirchhoff's second law. You can see the photons or the light source, they're interacting with a cloud of gas, and then after encountering a prism, they are forming a lot of dark lines. Now it might be quite interesting for us that in the previous case there was no dark lines, and here we have dark lines. So what's happening? So as you remember, in this slide we emphasize how the electrons are jumping from a lower level to the higher level, right? And then the same thing actually happens over here. Now you might know that the hot light source obviously has got a lot of photons. So each of those photons have got different amount of energy. So as they encounter a cloud of gas, so naturally the cloud of gas is bound to have some kind of atoms in the gaseous state, and each of those atoms are surely going to have some electrons. So the photons, which have adequate energy, they interact with the electrons and they push the electrons to a higher state. Okay, now not all the photons are able to do that. The photons which are able to do that, they lose the energy completely to the electrons, and those photons shadow you can see as dark lines in the spectrum. Whereas the photons which they either have lesser energy or higher energy than the electrons to push them, they simply pass through, and you can see that bright spectrum, and the resulting graph is visible as you see over here. The quite similar thing happens for the cloud of gas. Now here basically the photons which have adequate energy, they are released, and you can see most of them as bright lines, but the majority of the photons are already absorbed. Okay, and as a result you can see the majority of the spectrum as dark. So the absorption line spectrum and the emission line spectrum, they quite have got contrasting characteristics. A lot of times people, when they analyze an element's spectrum, absorption line and the emission line spectrum, they use this graph to analyze whether the element is same or not, and that's where this absorption line spectrum and the emission line spectrum becomes crucial to understand various spectra of various astrophysical sources. Okay, I'm coming to application a bit later, but first I'm going to talk a bit about the Henry Draper catalog. Now Henry Draper catalog is very interesting because it was the most voluminous amount of work ever done in the field of astronomy before the advent of computers. The story began basically from the works of Henry Pickering, who was basically working on the spectra of stars. He realized that I'm working on these kinds of stars, so I think I should classify them so that people later could work upon them. The Henry Draper name basically comes from a very famous spectroscopist who was working on the spectra of Vega cluster. Vega nebula, I guess. I'm not sure about that, but he was working on that. And in his honor, his widow basically funded the entire work of this particular catalog. So Pickering actually hired a lot of women in the Harvard Observatory. And if you look on Google, or if you look at various sites, you'd find that those particular women were called as the Harvard computers. Do not confuse with Harvard computers of today, because those women, they computed spectra of nearly about 220,000 stars. So the main criteria of categorizing them was basically on the basis of strength of the hydrogen absorption lines, how abundant the hydrogen absorption lines were from basically A to Q. Okay, and obviously the A ones are the strongest and followed by the weaker lines and so on. Okay, but interestingly, all that amount of work had no physical basis. It did not have any mathematical inclination, or they didn't knew how all those terms or how those values were related to each other. And that's where the work of Meghnad Shah comes in. The Meghnad Shah's work is not used or not much categorized today, but his work actually helped to reorganize the classification scheme starting from O up to LEM. Now this OBAFZ it was just random. There was no physical or any particular reason why they choose those names, but it was basically reorganized in terms of temperature starting from the hottest to the coldest. So the previous catalog was in terms of hydrogen lines, the next catalog is in terms of temperature, and then further refinement was done in terms of uses of luminosity. I have also provided a site where they have categorized all these 2 Lux stars, so I will come to that later on. So main thing, as I said, that Meghnad Shah's work was very much crucial into understanding the difference between spectra and the temperature. This is I found a book. It's basically named Introduction to Astrophysics. It was a book published by the Prentice Hall of India, and you can see the spectral type, the temperature, color is available, O5 to O9 starting from O to S, and the temperature is decreasing. You can see, observe them, and the color, and how the emission absorption lines are present, and what kind of stars you can see. So this is one basic idea of how it looks. I searched about the original catalog on the internet, but I couldn't find, so sorry about that. Okay, so this is the Saha ionization equation. Now Saha ionization equation was already present before Meghnad Shah did work on that. He did not invent this, nor he formulated this. It was already there. The mathematics was already there. The main crucial point of Shah ionization equation was basically understanding the ionization states in a stellar atmosphere. Now Ni basically means the number density of ion or number density of electrons or atoms in an ionization state, and Nn is basically the number density of ion in a neutral atom state. Okay, so a lot of this, and you can see that ionization energy is also crucial. So Meghnad Shah basically related how the ionization state or the excitant state are crucial in understanding them in terms of temperature and pressure. Now today we all know how temperature and pressure plays a crucial role in a stellar atmosphere or in the fusion of atoms in a stellar inside a star. But at that time he helped us to understand how the spectra and the temperature is very, very important. Interestingly, his work also helped us in formulating a new branch of astrophysics, that is the plasma astrophysics. So using the basic thermodynamics laws, that is temperature and pressure, he related the excitation and the ionization state in the atmosphere or the stellar atmosphere. Okay, and then we come across the Hertzsprung-Russell diagram. Now I'm not going to speak much upon this Hertzsprung-Russell diagram, but I'm going to emphasize that how Meghnad Shah's work, how his work of relating the spectra and the temperature was crucial in the formulation of the Hertzsprung-Russell diagram. Now Hertzsprung-Russell, both of them were independent physicists. Both of them were already working on this catalog, before Meghnad Shah's theory was there. But after they got to understand his equation and his formulation, they actually, you can included the spectral class. Now you can see, the absolute magnitude, the effective temperature, the luminosity, and the spectral class on 4 different areas. So don't get confused. They are not 4 different axes. You can basically use absolute magnitude or luminosity compared to the sun, or you can use the spectral class or the effective temperature. So they are basically the x and y axes. You can see below they have used the spectral class, right? So now O, B, A. So you can now understand that how the catalogs which Henry Draper formulated or his assistants formulated, and how Shah ionization equation spectra helped Hertzsprung-Russell to formulate their particular graph. I don't have very basic detailed idea about this particular topic, but I just wanted to show how the spectral class and how the Meghnad Shah's work was crucial into helping them to formulate this kind of graph. Okay, so the very basic topic of how the elements are analyzed, like we are talking about, okay, we're getting to understand hydrogen is there present, other elements are present in an astrophysical object. So how are people getting to do that? How do I know that this is happening? It's a very basic idea. You take an element, you heat it, okay, you observe its spectrum, and then you know how it looks like, right? So when you observe a star spectrum, you just compare it with it. Now the entire spectrum would match the 100% of the spectrum which you obtain in the lab and the spectrum which you observe from telescopes. They not match perfectly, because in the lab the temperature and pressure is different, the chemical might not be perfectly pure or something, that sort of. Even the telescope might have certain errors, but that's very basic way of understanding if it's have more or less the same element or not. Okay, and then this is a periodic table of the emission spectra of the elements, how various elements have the emission spectra. You can see that every element, they have got an individual and unique fingerprint. So you might ask that, okay, why do they have unique fingerprints, why not the same? Well, you might know that each of those elements, they have got a different atomic configuration, different electronic state. So on the basis of the excitation of the electrons from the lower level to the higher level, the spectra and the absorption and the emission lines are obtained. Okay, these are some famously known elements. You can see calcium, sodium, hydrogen, and you can also observe the the Balmer lines of hydrogen. Okay, and this is all in the visible range. So these kinds of fingerprints they use sometimes to compare with the spectra which is obtained from the telescopes and observatories. Okay, so I will just try to yeah, sure. I guess I'm not sure about that, but I think they somehow I mean they help to understand the evolution of a star more or less. I'm not very much sure.
The main sequence that you see there.
Yeah, yes, A section A.
Very strong predictor of the evolution of stars.
Yes, sequence A stars, right? Type A.
Exactly. So they have down and then they eventually leave and go into one of the other categories depending on the mass.
Yeah, I forgot to mention that the main sequence stars is basically the type A stars. Then the giants are the type B, supergiants are the C, and then the white dwarfs are the D stars. So sorry about that, I forgot to mention about that. And I also think that the main sequence one are the perfect examples of how adequate and how well behaved the HR diagram is, if I'm not correct. And then I'm trying to emphasize how spectroscopy today is now. We all use the visible light to analyze various spectra and understand the elements. But interestingly, today the whole matter has changed. Now you might have heard about multi-messenger astronomy or multi-wavelength astronomy. Okay, so the astronomers and the physicists are trying to map the entire universe over the whole EM radiation. So what is the use of it? I mean, why do I need to understand the universe in terms of radio waves, microwaves, and other waves? Well, mapping the universe in terms of visible light and mapping the universe in terms of other light helps us to understand how the astrophysical properties or various objects behaves in those dimensions too. It is going to help us to improve our theories, understand much better of how the universe works. And the entire way this is done is totally different by the traditional aspects. We basically have various tools and techniques of doing that, and that includes CCDs and gratings, analog devices. I think we have certain engineering students over here as well. I think they might have certain experience with the CCDs too, which are used in major extent in today's astronomy and as well as in other fields too. So radio spectrometry is one of the most interesting things which astronomers are involved with, and the way they collect data and analyze them is completely different to what we do in the lab in terms of traditional aspects. Okay, so as I said, we have CCDs and to disperse the spectrum instead of the traditional prism. Well, the most important and the most interesting thing about CCDs is that they can look at the sky for a long hours of time, 1 hour, 2 hour, 24 hours, 2 days, 3 days. So that help us to observe the astrophysical object irrespective of what their of what their how they look like, whether they have less luminosity or higher luminosity. So they used for a longer hours of time. The only difference is that a lot of light gets wasted. So that is still being worked on. New tools and techniques are still being thought upon. But most importantly of that, they help a lot in recording various astronomical images. So the main composition is basically composed of silicon wafer and capacitor, and they got lots and lots of pixels to capture every amount of light that falls in them. The working basically uses the photoelectric effect. The photons they get captured by the capacitors, and based on their energy content, they generate electrons, and how based on that they store data. And two people, Boyle and Smith, received the Nobel Prize for their work. Interestingly, it works off using a digital format image, and this is how it looks like. You can see a telescope, which is a CCD camera, and then the internal components of a CCD, and then even the Kepler Stress telescope has got lots and lots of CCDs. So it's interesting in that way. Okay, so the applications of astronomical spectroscopy. This slide I'm just emphasizing what areas they're used at, because I wanted to emphasize how they're used, how they calculate, but I couldn't find any particular there were a lot of research articles and research papers, but I still thought that maybe I don't have a proper idea for all those topics. So I just want to briefly go over how it's used. So we know the temperature they're used, we know from the Wien's law how they're used at, and then they're also used to understand how fast an object is moving in terms of the width of spectral lines. Okay, so you can see here, the sodium lines, they have got in the second in the second diagram, you see the sodium lines D1 and D2, right? They have got two absorption lines. So sometimes these lines which are together, they sometimes separate out. Okay, I don't know why they do that. I think there's a term called spectral line broadening. Okay, I'm sorry, I don't have a very basic idea of it, but that width of spectral lines help to understand how the material is moving. And then we have got the extrasolar planets and exoplanets, which help us to understand how life is over there and various distance to galaxies. We can also understand using the methods of light curve analysis to understand how an object is moving, or binary systems where two stars or one planet is revolving around a star, or two stars are revolving around each other. So the light curve analysis of those systems can be used using this particular astronomical spectroscopy. Okay, and then this is how an analyzed data from a CCD looks like. People use tools like like SAO. I think it's SAO DS9, which I think Sitara is quite good at, and I think other people might also be very good at. And they basically use various FITS images to analyze various data sets, and in terms of flux and wavelength, they obtain this graph. Okay, you can see the emission lines, right? It's a peak, and then absorption lines there are dips. So we know the wavelength of various elements, right? You see below there are wavelengths, right? So we know at which wavelength each element undergoes absorption or which element undergoes emission. So on the basis of that, we can calculate that which elements are present and which elements are not present, and that's how interesting the entire thing becomes. So just clicking on an image and then transferring it to a CCD and then making it a digital output and then analyzing using DS9 helps us to get so many understanding of what are the properties and how that galaxy that behaves. Okay, so as I said, an element has got an absorption line spectrum and emission line spectrum. Since the element is same, obviously its absorption line spectrum and emission line spectrum would have the similar features. You can see on the graph on the right hand side that at the point where they have the hydrogen line spectrum for hydrogen and the emission spectra, they are quite similar because they obviously are the same elements. So astronomers sometimes use this technique to cross check whether the element which they found in the first place is actually proper or correct or not. Okay, so the future of spectroscopy is quite interesting. Recently NASA's Jet Propulsion Laboratory is working on Everest NG, which has been a classic instrument which is being flown using aeroplanes and various other air flying objects, and it's expected to work on a large wavelength. I guess it's expected to work from 3000 nanometer to I guess 10,000 nanometer. So it's a huge application based project being carried out. Interestingly, this particular project is also being used in India to understand the properties of various minerals. However, use in terms of astronomy is still being thought about, how it can be used to understand various properties and various Earth-like objects near to the Earth's atmosphere. And then we also have the extremely large telescope, which I guess it's still being worked on, and I guess I think it's going to be inaugurated in just a few years. I still don't know about the current status, but the extremely large telescope is quite interesting one. Okay, and then they're also trying to work to use spectroscopy to understand the origins of life in terms of astrobiology and other extraterrestrial origins. SETI is a very famous, Search for Extraterrestrial Intelligence is a very famous institute in I guess California, I guess University of Berkeley, California, which is working on this kind of spectrographs. Okay, so I end this topic with a very basic idea of how even we ourselves can calculate a spectra of various stars, and that can be done even by having a DSLR. I saw on the Telegram page that a lot of the people they're posting images of various images of the night sky using DSLR. So having just a DSLR, any kind of DSLR, Canon, Nikon or Sony, will help you out to understand how the spectra works. So as I said, the camera lens is present over here for about 35 to 100 millimeter. You can use a star analyzing rating of about 200 or 100, and based on that you can fit it into your lens. Okay, and then you snap out the various photos. You take photos maybe of street lamps or the night sky. The interesting fact over here is a software called the RSpec. Now, the RSpec is an award-winning software that is used to analyze images. Even in labs we basically have various helium vapor lamp and other lamps in cardboard boxes, and then we see through a colorimeter and telescope to analyze how the spectrum looks like. The RSpec basically comes in two portions. One is that particular light box, and one is the software. So you can see you can have a fixed image, or you can click an image using a DSLR, upload it. Okay, on the left hand side you can see using a DSLR they have obtained a comet and a normal spectrum. Then on the right hand side, see, you get a spectra, even the value of the elements, at what wavelength they are present, you can obtain that. So it's kind of having fun with understanding the spectra and how it works. And they've also given which kind of camera they've used. Okay, this is another one. This is understanding for the case of hydrogen, and hydrogen alpha, hydrogen beta, and hydrogen gamma for the case of Balmer lines. So these are basically the absorption lines. Okay, and that's how I end up here, and just waiting up for your comments.
That's really good.
Thank
Thank you.
you.
That was super informative. So you can share your presentation on the group with maybe on the PDF.
Okay. I just want to know what can I include more, and I also had one more topic. I think I don't know if you know about this, but wait, I'm presenting. Is my skill available?
Yeah.
So this is I think found one, spectral energy distribution. It's quite interesting. They basically as I said, using the concept of Wien's law, they basically analyze a star, and then they use it further to understand the materials present around a star. Now I know of this because I was involved in a project. I actually had gone to Taiwan last year for understand star forming galaxies at high redshift. Okay, and this is what my project was about. So understand the star forming regions in galaxies. So a basic amount of project was involved with understanding the spectral energy distribution. Okay, this is how the spectral energy distribution looks like, and this uses the very basic concept of Wien's law. We have ellipticals, we have spiral galaxies, and this is the starburst galaxies where a huge amount of star forming regions are present. So you can see various lines over here, and the interesting part is that the SEDs, they match a lot with the black bodies concept. So but unfortunately I still don't have a very big detailed idea about it. So that's why I didn't include it in the site. I think you guys are more experienced with this one, so you can help me about it.
Right. So it depends on your job specialty. Maybe since we are covering operation astronomy,
Okay, okay.
so before that, anybody else has any specific topics in like you could understand?
Can I stop the presentation? I mean, my. And where can I upload the files in the Naxxatra community in Telegram or in the Google Classroom?
Better if you can read on that.
Okay, okay.
Yeah, so anybody else has any questions? So I think that was the one thing about spectroscopy is that it's much, much more complex than photogrammetry, right? And photometry, you are working with pretty straightforward visual data, right? Phenomena, actually, this memory, right? So I think we can put your presentation on paper. And I think